Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So today I'm going to share to all of you complete two electrode system analysis or electrochemical characterization for supercapacitor. My name is Hafiz. Welcome to my channel. The first analysis is you need to plot cyclic voltammetry of positive and negative electrode. From this graph, actually, you can compare the potential window from both positive and also negative electrode. So this is important. You can also include in your journal in supporting document, or you can include in the real document, means that in your manuscript. Okay, in order to explain what in this graph, you just explain what is the capability of your positive electrode, the potential window in this case from 0 to 0.5 volt, and for negative electrode from 0 to negative 1 volt. So that's why when we do a device, when we combine, we can show that the maximum potential window that can be achieved by the sample is 1.5 volt. For this analysis, you can also support by using some equation. For example, m minus divided by m plus equal to c minus times delta V divided by c plus times delta V. You can refer that formula to see the correct potential window estimation, and you can see from theoretical and also from your experimental, is it correct, the amount of potential window that you set. Number two is you can plot cyclic voltammetry at different potential window. So this at different potential window, you can choose whatever scan rate you want. For example, 5 millivolt per second or 50 millivolt per second. And here we want to double confirm the capability of our device to achieve the maximum potential window. That's why from this graph you can see I run from 0.5 volt and slowly I increase the potential window to 0.75, 1 volt, 1.25 and 1.5 volt. So from this, we want to determine the precise potential window of our main material or composite in supercapacitor device. Next is you can plot cyclic voltammetry at different scan rate. For this analysis, you need to choose your best material and plot at different scan rate. You can vary the scan rate from the lowest can be 1 millivolt per second or 5 millivolt per second, and the increment can be increment by 5, 10 or 20 until 200 millivolt per second or even more. You can see from this analysis, we want to see the number one is the shape. Whether your material show quasi-rectangular, in this case it's quasi-rectangular, or perfect rectangular, or it can show obvious redox space. Okay, depends on the shape. First, we are going to see the shape. In this case, the shape is quasi-rectangular, suggesting that the electrode were properly mass balanced. Okay, then from here, you can also see whether the shape deviates or not upon increasing the scan rates. Okay, that's also the important thing to see in this graph. After that, you need to evaluate that graph. You need to calculate from that graph, you calculate area under the graph, then you can get the specific capacitance. And this analysis is plot line graph of specific capacitance versus scan rate. Okay, you can see the trend of your material. At low scan rate, it produces a high specific capacitance, in this case 392 farad per gram, and slowly decrease upon increasing the scan rate. So you need to give some example why, what happened, why is suddenly the scan rates reduced. You can say that it can be noted that the decline in the specific capacitance at higher scan rate is due to the insufficient time and also non-utilization of the whole active mass with electrolytic ions. In simple, in simple way means that the electrolyte ions does not have enough time to travel or diffuse or to permeate to go through the surface and also the bulk of electron. Okay, that's why when you increase the scan rate, the millivolt per second increase, the amount of voltage per second increase, the ions does not have enough time to going through the surface of the electrode, even the bulk of the electron. That's why the specific capacitance is lower because unutilized space in the electrode. Next, cyclic photometry finish. You can go to the galvanostatic charge discharge. Number one, you should plot GCD at different potential window. This one to support your cyclic photometry. So again, we want to confirm the precise potential window that your material capable to achieve. Then you plot the galvanostatic charge discharge at different current density. It is recommended to go from one above because most of channel prefer high current density. But if your material can go a lower current density, you can go to 0.5, even you can go to 0.2 ampere per gram. Some material for the device, they are incapable to go low current density because at low current density, you supply minimum or you supply lower current. Sometimes that lower current cannot achieve the potential window for the device that you set. Okay, when the potential window is not achieved, then no point you run the GCD. That's why you need to slowly increase the current, means that the current density also will be increased. Okay, this is ideal case. Sometimes people didn't report from maybe 1 ampere per gram. The current is not enough. That's why they run for 2, 3, 4, 5, 6, 7, 8 ampere per gram. Depend on the material. If you cannot get a very good shape, you need to increase the current. And in this case, you also need to see or measure the shape of your GCD. You need to explain, is it the perfect triangle, slightly distorted, and what mechanism it belongs to. Next, from the GCD, you can get the specific capacitance. From that, you can calculate the specific power and also specific energy. Then you can plot the Regen plot. Regen plot is actually specific energy versus specific power. It doesn't matter where you put the y-axis specific energy or y-axis specific power. Some journal put like this, some journal put the other way around. Okay, you can choose which one you like. But most of the journal, the y-axis is specific energy, the x-axis is specific power. Then you need to compare with the literature to see the performance of your device. The literature that you need to compare should be the literature that have a slightly common with your material. Then you can claim that your material is the best. Then almost at the end of the part, you need to plot stability retention. Okay, a lot of people might curious how to plot the stability retention. You can use two, maybe three steps. Okay, the number one technique, what you can use cyclic photometry, whereby you run, in this case, from 0 volt to 1.5 volt, you run for 10,000 cycle. 10,000 cycle is a common practice nowadays. If your material cannot stable until that, you can go until 5,000 also can. But some reviewer demand for high cycle number. Okay, for cyclic photometry, just increase the number of cycle. From normally you run 1 cycle or 2 cycle, right? So in this case, run for 10,000 cycles. Then don't choose slow scan rate. You can choose 100 millivolt per second or 200 millivolt per second. You need to have a faster scan rate there, so your electrolyte will not dry up during the process. Okay, that's using CV. And then your skill number 2, you can use GCD. In this case, I'm using the GCD, whereby I run the GCD at 10,000 cycle. So then what I did, I plot the first cycle and also the 10,000 cycles GCD plot to see a comparison. And to do or to calculate the retention, first what you need to do, calculate the first cycle specific capacitance. Then at the subsequent cycle, you just divide by the first cycle and times 100. Then you can see how much it can retain. Let me give you an example. For example, at first cycle, you get 100 farad per gram. And then at 10,000 cycle, you only can retain 80 farad per gram. So you are losing 20 farad per gram. Means that you can retain only 80% of your initial capacitance. Okay, that's how you calculate the stability retention. Okay, last but not least, you need to plot the EIS before and after the stability. Sometimes the trend vary because before the stability, you can see that the semicircle is bigger, the Waback line is shorter. You can see that before because of height, faster electron transport. So after the stability test, what happened? Your Waback line become longer because now we observe some resistance, some loss of capacitance from 100% now become 84%. So 60% of capacitance is lost, maybe due to resistance. That's why our Waback line become higher. In terms of charge transfer resistance, during charging and discharging, what happened in the material, some material or composite is activated. That's why the charge transfer resistance, some cases, is become smaller. Okay, in the RS, maybe the RS, there's no much deviation. Okay, so that's what happened. But in certain case, you can observe both Waback and also RCT become bigger and longer. So depends on the material. So I think that's all what you need to plot for two electrode system. A simple two electrode system for supercapacitor. By having all this analysis, you can start your experiment and publish a results on the supercapacitor. That's all. Thank you very much. You guys awesome. Bye.